Hello, everybody. I'm going to go over the signal conversion homework, but I'm going to go over this whole thing. It's going to be in 4 parts, I'd guess. Okay, first part is asking us about a 5-bit flash converter. That's the ADC. If the voltage range is 1.5 volts, what is the resolution? There is an equation on the data sheet, which I'm going to show you now. However, I would prefer if you sort of just understood what was going on. Where are we? And this one here. So the resolution is the input voltage range divided by 2 to the power n, where obviously n is the number of bits. So I will write that down. I will write that down for you. So resolution is voltage range over number of 2 to the power n. So in this particular case, it's 1.5 volts divided by 2 to the power 5. So that's 2 to the power 5 is 32. I think I just got my answer here. Be easier. 0.047. Okay. Okay, it's asking exactly the same sort of thing here. So obviously, it's going to be 2 to the power 10. And this time after the input voltage range. So obviously, the input voltage equals, as I say, just rearrange the equation. Look, L shape 2 to the n goes up there. So it's a resolution 0.04 multiplied by 2 to the 10 gives me 40.96 volts. Okay. Right, this is a bit of a different one. It's basically saying what it says an ADC has that resolution. There's the input voltage range. What is the number of bits needed? So first of all, I'm going to obviously go for um, find the number of bits needed. So the 2 to the n bit essentially. So the 2 to the n bits is rearranging the equation. It's just a bit above. As you can see there, if I made that the subject, it's going to be input voltage range, which is 2 divided by 500. Look, it's micro. The old unit thing always comes in, doesn't it? I know that number is 4,000. So what's the number of bits needed? So 4,000 total bits. Okay. So what is it going to be? Well, then you need to kind of do a bit of trial and error. You can rearrange the equation, but I'm just going to show you this. 2 to the power 11. Yeah, 2 to the power 10 is 1,024. 2 to the power of 11 is 2,048. 2 to the power 12. Keep going till it kind of goes over the 4,000 mark. Is 4,096. There you go. Therefore, 12 bits needed. Okay, so 12 bits would be needed. That's the therefore there. So basically just keep going trial and error until you go beyond the 4,000. Okay, I'm not going to bother drawing that because I've got one a little bit below. I can straight away tell from this table, though, that the resolution is 0.25 of a volt, quarter of a volt. That's the resolution. I can straight away say that. Okay, so how to interpret this table? So obviously, as the voltage increases, the voltages there become 12 volts. So as you can see, look, the first one's become 12 volts, then 2 of them become 12 volts, then all 3 become 12 volts, and that's when you got binary 3. Hopefully that makes sense for that. Basically, what are the suitable resistor values? We'll just have a little look. It's a 1 volt reference and it's an even voltage across each. So why don't we just go for the bog standard? You could even go even each. You could actually make them like what was it, 0.25 of volts? So you could make them 25k each if you wanted to. Okay. Okay, so this is another one. So that was basically, if you look at the circuit diagram, that's the solution for the one above anyway. So why do we need a priority encoder? A priority encoder converts the outputs from the op amps onto a binary number or into a binary number. So converts the output voltages from op amps to a binary number. And that's when we've kind of looked at the logic. When we did it like we did it with logic gates and XOR gates and things like that. Okay. The comparator labeled W it's an overflow indicator, but what actually does it do? It will indicate if the input voltage exceeds the reference voltage. Indicates when the reference voltage, sorry, the input voltage when V in exceeds V ref. Okay, that should be in. Yeah. Okay. What is the resolution? That's the smallest voltage step. Well, look, they're the same size resistor. There's a 2-volt supply. It's going to be a quarter of 2 volts, isn't it? Yeah. You use Ohm's law. Use ratios. Yeah. So 2 divided by 4 equals 0.5 volts. There's my resolution. What is the analog input voltage range for this? Well, it's going to be 2 volts because you don't want the analog input voltage range to exceed the reference voltage of 2 volts, do you? Okay. Part D, reference now is reduced to 1 volt. What effect would this have on the resolution? Would it increase or decrease the resolution? It would actually decrease, so it would half, in fact, if you want to go proper. So half or halves. The analog input voltage range, that would also be halved as well, then, wouldn't it? Yeah, to 1 volt. Okay. Right, this one, where is it? The resolution. Sorry, the comparatives have a saturation voltage of 6 and 0, so we need to go to 6 and 0. The reference voltage is set to 1, so that's telling me my resolution is a quarter of a volt now. Hope that makes sense. And then obviously we want to change, so which one goes first? X is going to go first. When we get to a quarter of a volt, where's that? I'm going to say there-ish. So now it's going to go up to a logic 1. When we get to half a volt, there. This one's going to go to a logic 1. Look how easy this is. It's just obviously seeing the questions makes you a bit neater than me. When we get to 0.75 of a volt, which is about there-ish, we will go up. About there-ish. We'll go up. Okay, that's that one done. Okay, so this has given us a load of information. We basically need to design this. Now, I've already made the circuit diagram for you, but let me just show you. So it's 2 bits. So we're going to need, obviously, 4 resistors, 3 op amps. Input voltage range is 3 volts. Okay, so basically we can work out resolution quite easily by doing 3 divided by your number of bits, 2 to the power n. Yeah, input voltage range over that equals resolution. So that's 3 over 4. So it's 0.75 volts resolution. That's just from that equation that we've been using. Hope that makes sense. Comparator outputs of that. Right, so what we need to do is we need to first of all design it. At the end, we're going to look at some Boolean expressions. So let me show you how to do this. There's your design. So we've got 3 volts at the top. I've added the overflow indicator. Can't remember if it specifically asks for that, but I'm adding it in anyway. There's your priority encoder, so we're going to have to work this out in a bit. And the resolution is 0.75 volts, so it's even-sized resistors there. So that's that one. Hopefully that makes sense. Okay, right, so the analog input voltage is going from, it was 0.75, 0.75, 0.75 to 1.5, 1.5, 2.25, 2.25, 3 over 3. Okay. Comparator outputs, have I labelled them? Usually we label them, haven't, but usually we'll label them X, Y, and Z. So I'm going to label them X, Y, and Z. That's the usual one we use. X is the first one, Y the second one, Z the third one. So with nothing going in, we want nothing. 12 volts there. Ooh, 12 volts there, 12 volts there. And 12 volts there, 12 volts there. And 12 volts there. Okay, and then obviously binary 0, 0, 1, 1, 0, 1, 0, 1. Take true table for the priority encoder. So comparator outputs now have given us, sorry, that's my comparator outputs there, isn't it? Yep, sorry, that's my comparator outputs there. So I'm going to write them now as logic levels now from a thing rather than 12 volts. So we've got nothing. We've got 1, 0, 0, got 1, 1, 0. Right, how do we do this? Let's have a little look. Let's do my B's first. Right, B, first of all, I always say, does it look like either X, Y, or Z? I can straight away see that B is exactly the same as Y. A, so we're looking for unique things now for A. Unique things. There's A. Oh, that's the A bit there. That's the A bit there. So is there anything that we can sort of say that's unique there? Well, look, what can we say? We can say, we could say that X and not Z happen. 1 and 0. We could say, where are we? That's for A, isn't it? Where are we? So we could say that that is the case. Oh, hold on, I've done it wrong. That's why I was thinking. Hang on a sec. It's not as easy as that. I know what I've done wrong. Deliberate error there, guys. That should be a 1. I was going to say it wasn't that easy when when I looked at it before. Okay, so you could look at that and look for unique things. However, if you're unsure, use the old Kano map. So I'm going to put this into the Kano map, to be honest. So let's have a look. So location 000, I put a 0. A location 100, where X is a 1, I need to put a 1. 100. A location 110, I need to put a 0. And finally, at location 1, I put a 1. All the rest become don't cares. Don't cares mean you can group them, you don't have to group them. So X, 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 and X. Don't cares. Okay, so I can see 2 groups here. Okay, so I can see 2 groups of 2. I think best ones I can see there. Okay, so you can go for this one. It's a group of 2. So that one is, so A equals X and not Y. Okay, that one okay, X and not Y. Or we've got a choice. You can go up there, you can go Z and Y and Z if you went up the top there. Or we could go that way again and go X and Z. We could, look at that, we could take the common factor out of this one. X, not Y. Where are we? Not Y or Z. Is that right? Z there. Okay, I think that's that one there, which you can have. Another way you could do this before I sketch it as well, I'm going to do it in a different colour, is by looking at, again, the unique things. So I'm just going to try and do the unique one now. I can see that that is unique. That only happens there. So that is X and not Y. You may have seen I've already written that down. Or something that's unique that happens here. Okay, what I've got is Y. Well, I can use where are we? I can use Y and Z. Y and Z, or I could have used X and Z, which is the one I just saw. But I'm going to go for Y and Z. There you go. So that is another way you can do it. I've looked for unique things. There you go. Look, that's unique as well. So if you're happy with doing unique things, that's good. Or if you prefer to use the Kano map way, that's also fine. Both would be absolutely fine. Okay, and then fine, it's asking us to draw it. So let me just show you how I would draw this. B A. I'll draw the I'll draw the top one. Yeah. So how would I draw that? So I want to end with B and A, don't I? So B and A. So we've got X,